All right, section 10.1 is titled Conics and Calculus. A fair bit of what we do in this section is a bleed over from trig. It's where you tend to have encountered conics before. Sometimes they're also encountered in an algebra course or maybe a pre-calculus course that you've had. And so pieces of this are going to look, most of it probably even should look familiar. And then there's going to be some new pieces in there as well. So we're going to start with each of these has equations. One of our conics is actually a parabola, but we're encountering the parabola from the standpoint of conics, which means it's not from the standpoint of algebra. So the standard formula of a parabola with vertex hk and directrix, and I'll draw a picture for these in a second, y equals k minus p is x minus h squared equals 4p times y minus k. This is if it's a vertical axis parabola. And then we have the corresponding one where we do it as a horizontal axis. And the directrix is x equals h minus p. The equation is y minus k squared equals 4p times x minus h. So we have this thing called a directrix. We also have a piece called a focus. The focus lies on the axis, p units away from the vertex. And then the coordinates of the focus are as follows. If it's a vertical axis, it's h and then k plus p. And if it's a horizontal axis, it's h plus p and then k. So fill in those gaps or the details if you're writing all of it out. And I'm going to draw a couple of pictures so that we can make note, anyway, of where these quantities are showing up on the picture of the parabolas that they're describing. So let's start with this one. Yeah. So we're going to start with the one that's the typical one that you've seen before, which is that it opens up or down. We're going to draw ours opening up. Maybe get a little bit closer so that I can make it work a little bit better. The dotted line at the bottom here is called the directrix. I'll describe a little more about it in a minute. But that's what it is. It's a directrix. And there's a distance right here, which is p, that's between the vertex of the parabola and the directrix. And if you go in the opposite direction, that same value, p, you end up at this point right here, and this point is the focus. So the directrix is on the outside of the parabola. The focus is interior to the parabola, but they're the same distance away from the parabola, okay? I think that's probably good for now. Let me draw the other picture. So the other picture has parabolas that open left or right. Yes, sir?
Is the focus also like a line that goes through the parabola?
Nope, the focus is a point. Yeah, it's an ordered pair, like down here. These are our focus points right here that are given. Yep. Okay, so far so good? All right, the other parabola that we're going to draw is one that would open sideways. Oops, the wrong tool there. So the directrix is actually a vertical line now. So here's my directrix. Here we go. And the parabola opens like this. The distance again right here, let me choose a different color so that it can specify it. Not with that tool, with this one. This distance is p, still away, and there's an equal distance over here, p away, and we end up right here again at the focus. So this is my focus that is interior to the graph of the parabola. I'm a little bit sloppy. My parabola should have arrows on the end, and technically so should the directrix. A couple of things. The one that's at the top you're most familiar with. That's a function notation. Algebra is done with functions, so that's the one we see happening in algebra. It's presented a little bit differently here, but we see it happening still. Of course, if this is the p-value, it tells you how the direction is that it opens. So if the p-value is positive, it's opening up. If the p-value is negative, it opens down. Okay, so I'll just write one of them in because the other one's clear. But the sideways one requires us to actually state it because this is not one that we work with in algebra. So if the p-value is positive, this one opens to the right. And if it were negative, it will open to the left. Okay, So the form, or the formula, if you will, they look a little bit different, right? They're not solved for y equals or x equals. They're actually showing by the ordered pair notation very concretely where we have the vertex, how we can find the focus, and how we can find the directrix. So let's do an example so you can see how it works, okay? So here's one that's given. What's being squared here? Is it x or is it y?
Y.
It's y. So if you take a look at the two formulas that were given, the one that's got y squared and it's the one that we're going to be mimicking. So whichever piece is squared, that piece with all of its glory, right, all the piece associated with it that's being squared stays on one side, and the other piece, it moves. Now, for the sake of what I'm doing here, I'm actually going to move my y minus or 1 to the other side because it's negative anyway, and I'm going to move the other piece over. So I have 4, it's x plus 2. We're going to shift the minus 4 to this side, so that'd be plus 4. And we'll shift the y minus 1 squared to the other side. Okay, is that all right? Everybody good with that? Okay, let's see. We would like to simplify the left-hand side a little bit because right now we have a kind of a double addition thing going on. So we have 4x plus 8 plus 4. And then the right-hand side can stay as y minus 1 squared. We do not want to distribute that and multiply it out. It's in a nice form. Okay, we like that form. On the left, then it's 4x plus 12. And the 4 can be factored out then to be 4 plus 3. Okay, so we've achieved the form that we were looking for. We're looking for a couple of things, actually. So we're looking for one side to be squared, which we have that on the right. We had that as soon as we shifted it over. On the left-hand side, we're looking for this to be in factored form. But in particular, if you take a look back over here, we kind of like it to be expressed with a 4 in front. If there's not, we're okay. It's okay to manipulate with that. But notice 4 is a part of the formula. So the fact that that 4 is showing up is actually kind of embedded in the formula as it is. So when we're looking then at our vertex and so forth, can you tell me from this information, what is the vertex of our parabola? It's just like if you're looking at circles or anything like that. It'd be negative 3 and then 1, right? So the values that are associated with the x and the y here in their opposite signs are going to create the vertex. Okay, that's not the focus and the directrix, that's my vertex. But that actually gives us a fair bit of information that we could start a graph going if we wanted to. We could also establish how this graph is opening. So this graph, is it opening left and right or up and down?
Been down.
Careful.
That's what I thought.
It's left and right. How do we know?
It's gotta be the
That's not y.
It's for solve for y.
Because what's being squared?
Y.
Yeah, the y is squared. So because the y is squared, this is going to open either left or right. Okay? How do we decide if it's opening left or right? Well, we base that on our p-value. What is the p-value of this? I mean, we didn't write that down, so let's actually do that. Okay, comparison, back to the original formula. It's 1. In particular, for the purposes of what we're discussing right now, it's positive, right? So how will this graph open, left or right? It'll open to the right. Okay, so the basic shape of this graph looks something like this. It's opening to the right. Yes, sir?
P, is that just because 4 is not, 4 is 4, so that means P is 1, right, from the equation?
Yeah, so if you take a look back at the equation, let me shift this down here and I'll put it in here. The equation says 4p times x minus h equals y minus k squared. So if we're pairing these up, this 4 and the 4p are equaling each other, so p is 1.
So if it wasn't 4,
Yeah, like let's say that the 4 weren't there and it just said nothing in front of it. Well, then the p would have to equal what? 1/4, exactly. So you're essentially setting what's in front of this equal to one another. In particular, if there's not a 4, then you're going to have to compensate for it within the p-value itself. Do you have a question, Dylan? We're good? Okay. All right, so far so good? All right, p is 1. P is 1. So let me make a mention too. So there are some things in here that are very formula-based. And if you really like formulas and memorizing formulas or going off of formulas, that's fine. I don't think that way. I think in terms of graphs. So if I can picture what's going on, I'm far more likely to have the things in the right location and to get the right values. So that's the way I sort of lean to when I'm trying to find things. Like, for example, over here, there's some formulas for finding the directrix and finding the vertex. And you're welcome to do that from those formulas if you wish. I feel like that if I can draw the parabola, which we have, right, based on those details, what value is p and which one's being squared, then I should be able to look at the other information and plot the vertex, the focus and the directrix, and then create equations from there. So that's how I'm going to show it to you, but if you don't like that approach, there are other approaches that you can do this with.
So on the test, we can do either way?
Mm-hmm.
Okay.
So what is the p-value? Well, we already found it, it's 1. And from a visual perspective, I already talked about the fact that p is actually the distance from the vertex to the focus and the vertex to the directrix. So from here, I should be able to simply plot those values. So if I move 1 to the right, in this case, that's my focus. And if I move 1 to the left, I have my directrix. And I can draw those in like this. And then I can actually go back and get equations or point values for those. So what's the equation of the directrix? Where am I? Yeah, I'm at -4, and it's an x value, right? Like everywhere along that line, the x value is -4. So this is x equal -4. And what's my focus? -2, 1. So I don't need a formula to be able to do that. All I really needed was the p-value, and I'm going to have to graph it anyway, so I might as well graph it and then just read it off the graph.
Wait, so it uses the formula of a horizontal axis, because that's where it's opening up on?
Yes,
Okay.
exactly.
Just wanna make sure.
They're describing it. Adrian's noticing something. So they're describing the axis here. It's not, the descriptions of the axis are not they're not directly based on how the directrix is working. They're sort of in opposition to that. They're right. They're actually talking about how the graph is opening. Is it opening with a horizontal approach, or is it opening with a vertical approach? So, and they are doing it based on that. Okay, you ready to look at an ellipse? Of course you are. Of course. All right, next one, ellipse. Standard equation of an ellipse. So the standard equation of an ellipse with center HK and major and minor axes of lengths 2a and 2b has this formula. X minus h squared over a squared plus y minus k squared over b squared equals 1. And again, I'm going to take a slightly different approach that your book does. The reality is, whichever number is bigger, a squared or b squared, determines the major axis. I don't need extra formulas to decide. I can simply look at the numbers and know. If the number under the y value is the biggest, that means it's going to be oblong in the y direction. And if the number underneath x is the biggest, it's going to be oblong in the x direction. And then the foci lie along the major axis, whichever one it is, c units away from the center.
So like if a squared is bigger, that's the major axis?
Yep, exactly. And then we do need a quantity. And again, we could be really particular and talk about c squared is a squared minus b squared, or c squared is b squared minus a squared. But if we just stick absolute values on them, it doesn't matter which order we subtract them in, right? C is going to be a positive quantity. It's a distance. So it doesn't matter how we subtract. We're going to take the absolute values anyway, and then that takes care of us needing to have two formulas and worrying about which one we're going to use when, because we're just going to take the absolute value. So let me draw a couple pictures on this one as well. So you know what? Let me start with the pictures of the ellipses themselves. So we have two options. One option is the ellipse opens like this, so it's sort of longer than it is tall. And then the other option is that it's, I'll move that, sort of taller than it is long. I'm still on screen, so we're good. No, I'm not.
So
Let me just make it smaller.
with the one where it's longer horizontal would be when a squared is bigger, right?
Yes,
Okay.
exactly.
I'll put that in my notes.
Yeah, so, and we'll draw it that way too. So here's my center, right? This is HK. And that's the same no matter what type of an ellipse we have, right? Whether it's a vertical ellipse or a horizontal ellipse. This is my center, HK. And then we'll draw in the axes with some dotted lines. So these axes are creating for us how sort of oval, if you will, that the shape is. There we go. And then this one. And this one, not too bad. So visually, you can talk about the fact that this graph has a major axis that's horizontal, right? You see it. It's larger. I mean, so its major axis is horizontal. So if we're taking a look at the major axis being horizontal, then these points here on the edges, right here, are found by taking the distance away that's related to the value underneath x. So what is listed as in the equation underneath x? A squared, right? And so these distances are a away. And the value listed underneath y is b. So these distances are b away. Now notice I'm not putting these ordered pairs that have the direct equation or the direct formula maybe for a and b with them, because it's based on where you started with your center. If the center is at 0, 0, then this would be negative b, and this would be positive b on the y values, right? That's easy enough. But whatever the center is, we're just going to add b and subtract b to find the y coordinate for the top and the bottom of this one, which is the minor axis. And for the major axis, to the x coordinate, we'll subtract a and we'll add a to find those coordinates. And then over here, there's a c value in each of these locations. And it's always located along I shouldn't call it like that. Let me designate it like that. This is C. Because I want to make sure we can draw this as though it's not necessarily centered at 0, 0. It's a distance C away from the center, but it's always along the major axis. Okay, the distance away from the center, that's our foci. And the foci give us some indication or some measure of how oval the ellipse is. It's the ovalness of the ellipse, okay? And we can draw all of these same pictures over here. Notice I am choosing, the way I've described this, to still let this be A away. Actually, I'm calling it a positive A. It's just a distance, right? So it's A away. And this one are still B away. But on this picture, the B value is clearly longer than the A value. So C is going to be represented along that major axis, which is now a vertical axis.
They get a C value more oval.
What's that?
The larger the C value, the more oval it's going to be.
Yeah. So we're taking a look then. Let me see if there's anything else I want to make mention of. I didn't label them. Maybe I will. I labeled all my A's, B's, and C's. So let me just label one of them. I won't label both graphs because they're similarly labeled. But we call this point and this point the vertices. So the vertices are along the major axis. We call that point and that point, established by C. Those 2 points are the foci. That's plural of focus. My graph is getting messy. Let me use another color at least. So this axis here is my major axis. Smaller pen. And this graph would be my minor axis. I'm pretty sure y'all have more room to write than I left on my screen. And we have a similarly labeled graph if we did it on the vertical one. All right, any questions so far? You're about to do something that you know and love, and you've already fussed before once this semester when we've done it. Nope. We have one more definition before we get there. We're going to graph, correct, eccentricity. So eccentricity or eccentricity, I don't know that there's a definite which way you're supposed to pronounce it, so go with whichever you like, is the measure of the ovalness of an ellipse. It is found by taking E equals, and this is not E as in the E that you know and love, right, 2.718, ... whatever. It's not that E. E stands for eccentricity there. Equals C over A. C is the distance from the center of the focus, and A is half of the length of the major axis. And please note that they're describing, or the way that it's being described, is it is half the length of the major axis. So it's not necessarily the A that I called A, which is always along the x-axis. It's the major axis length. So in our first picture, the E would have actually been, with the letters I described, C over A, but in the second graph, it would have been C over B, because B was the length of the major axis, or half the length of the major axis, which I meant to say. Okay, so it's either C over A or C over B, depending on whichever one's the major axis. We'll call it like that. I think that'll work. Okay. All right, so here is an equation. It is an equation of an ellipse. Can you tell me how you know it's an ellipse from what we've done or described so far? Why is it an ellipse and not a parabola? Let's go with that. Yeah. X and Y are both squared, right? Parabola, you have one of them squared, not the other one. They're both squared here. Now, we want to be able to find all the things we just described, but the form in which it's given to us is not a very friendly form in which to find those things. We need to change the form. How do we go about changing this form?
Complete the square.
Completing the square. Okay, so we're going to group the pieces together that will be grouped, which will be my x's and my y's. Y doesn't have a counterpart, but x does. So I've got x squared minus 4x, and then I'm going to have to put something in this space. My 9y squared stands alone. There's a 5, and then I compensate on the other side. So in completing the square, what's going to go after my negative 4x? Yeah, it's going to be an addition of 4. And if I add 4 to the left, I have to add 4 to the right, which makes it a very friendly value on the right, actually. You'll see why in a second if you don't already. All right, on the left, how does x squared minus 4x plus 4 factor? X minus 2 squared. Is that good with everybody? Excellent. And then I have 9y squared, and now it's going to equal 9. What else do you notice if you flip back and look on the first page that's in the form of the ellipse that we don't quite have yet? I don't have an a squared and a b squared yet, but it's because there's not a 1 on the right-hand side. I need it to say equals 1 on the right. And once I change it to have the equaling 1 on the right, then I will start to see that a and that b coming forward. So we're going to divide each piece that's squared, which is in essence both sides, by the number 9. So on the left, that's great, like the x component. That's 9. If you want to write this as 3 squared, that's even a little bit friendlier just for identification purposes in a moment. In the middle, though, the 9y squared divided by 9 would actually just give me y squared. That's not the friendliest way to write this. It'd be friendlier to write this as y squared divided by 1 squared. And whether you choose to write it there or not, it's there, right? That's the identification we're going to make in a moment, and this is going to equal 1. So we're going to identify several things. It says the center, foci, vertices, and eccentricity, and we're going to sketch it. We're going to do a lot. So let's actually start with the center, because we can read that off of the equation. What is the center of this ellipse? 2, 0. And I'm going to draw as I go. I say that. Let's get this solid. Okay, so we need to center at 2, 0. So 2, 0 would be about right here. All right. Now, the values, I know we have to find foci and all the other list of things, but I'm going to work on the graph because some of these things will come about from the graph, just like the focus and the directrix did on my parabola. So if I look back at this graph, the 3 and the 1 are important features. What do the 3 and the 1 tell us? Yeah, they tell us how far we go out each direction, which is then going to give us our major and minor axis, right? So the fact that it's 3 squared tells us that from the center, which I've already plotted, I'm going to go left and right 3. So over here, I'm going to go left 3, which puts me here, and right 3 puts me about right here. Okay? And then what about on Y? Yep. We're going to go up 1 and down 1, again from the center. So that's my orange dot. I did it in different color on purpose. And in terms of drawing this ellipse, I need to connect the 4 yellow points, right? I've got a tool. I know, you don't have a tool for that. So it looks something like this. But from this picture, you should now be able to read off several of the other things that were asked for. The next thing after center that was asked for were the foci. We don't have that one yet. So let's just skip that for a moment and move to the third one. vertices. We do have those. Okay, so which ones are my vertices? They're the ones along X, right? It's the major axis ones.
1, 0.
So we have negative, whoa. Goodness gracious. Right here, negative 1, 0, and 5, 0. So we have our vertices at negative 1, 0, and 5, 0. And this is off the cuff, but I'm fairly certain this is true. There is a name for these other 2 points, and they're called covertices. We're generally not asked for them, but just FYI. And then the next one says, so we did center, we did vertices. Eccentricity, well, we need to know the foci values before we can do that, right? Because that actually is part of that equation. And then it says to sketch, we've already sketched. Okay, so we're back now to finding foci. Well, foci actually is found by having the c squared value, and it's the difference, the absolute value and the difference between a squared and b squared. So you can write the absolute values if you wish, but you can also just put them in the order that's going to give you a positive if you wish as well. I'm going to have 3 squared minus 1 squared. What's that going to give me? It's going to give me 10. Okay, but it's c squared is 10, so what's c? It's a square root of 10. Now, square root of 10 is approximately what? Did we write that right? There's subtraction. Is my formula wrong? No, I wrote it wrong here. I think I wrote the 10 and it meant to be 8. I added instead of subtracted. My apologies. Does anybody know why it red flagged me? That's a good question.
Because you have it written down there.
Nope, it's not. When we graph it, I'll show you. All right, so what is approximately square root of 8? Because we're going to graph something with this. What is square root of 8 approximately?
2.2.
Is it 2.2? I don't know. It's 2 point something. Somebody grab a calculator. 2 point. Do you think it's between 2.2 and 2.3?
No, between 2 and 3.
It is between 2 and 3. You're right on that.
Yeah.
That's for sure. It's 2 point something.
7.
I think it's probably close to 7.
2.67.
Adrian's going to let our calculator give us an approximation. What's it say?
2.82.
2.82. We were close. It's almost to 3, right? All right, so I'm going to do this one in orange as well. So we take our center point, and we're going to go out along the major axis, 2.8-ish, right, in each direction. Here and here. These are the ordered pairs for my foci. Does anybody now know why square root of 10 red flagged me? It would have been outside of my circle, or my ellipse, yeah. Square root of 10 would be bigger than 3, and we would be outside of my ellipse. That's why I knew I made a mistake. I mentioned it because you should pay attention to your own mistakes and know when you're making them, because they wouldn't graph right. That was the one that was a red flag to me. Okay, cool. We need to find the foci, though, in terms of an exact value, not just graphing it. So how are we going to find our foci when we have this center point and we have these 2 points we've plotted? What was that, Adam?
2 plus or minus square root of 8.
Okay, so we have 2 plus the square root of 8. I'm going to write it separately just because I'm going to have and 2 minus the square root of 8. What's my y value for those? It's still 0 just because I'm on the x-axis, right? If you want to write plus or minus, that's fine. I don't know if WebAssign will accept plus or minus. If it does, great. If not, write it separately. Sorry, 2 things. What was yours, Adrian?
Oh, sorry.
No, there's 2. It's okay.
Why do 2 plus? Square root of 8?
Because I'm at 2 when I start.
Oh, okay.
So I'm at 2 and I'm going square root of 8 to the right, and I'm at 2 and I'm going square root of 8 to the left. Okay, Ben?
Do you prefer that form or decimal form?
You want to exact. We do not want decimal form unless we're told to take a stand and do decimals. Yeah. So we're going to do it exact when at all possible. All right, we've got the foci, we've got the vertices. Eccentricity, that's the last one. All right, so eccentricity, E, is going to be the ratio along the major axis of the foci value, right, the distance we got for C, which was square root of 8, divided by my length all the way out to the vertex, which was 3, right? So what is square root of 8 divided by 3 approximately? Well, there's an approximation we could get, but there's no way I can simplify that exactly, correct? So for the purposes of what we're being asked for here, we would simply leave it as square root of 3. That's not true. Square root of 8 can simplify. We need to do that part of it. I was thinking about the fact that we weren't able to simplify it with 3. We can't simplify this square root of 8. So this would be 2 square root of 2 over 3. And let's go change that in our foci as well, because I did not catch that before. So plus 2 square root of 2 and minus 2 square root of 2. All right, that's better. I think that matches everything on my paper now, so that's good news. Okay, any questions on that? Okay, ready for the third conic? All right, our third conic. What happened here? Just a second. This is just titled wrong. This should say hyperbola. Okay, is the standard equation of hyperbola, of a hyperbola even, not an, a hyperbola. So the standard form of the equation of hyperbola with center HK looks a lot like our ellipse, but what's different? It is subtraction. That is the only difference. Because of the way that we're going to create our equation for C and stuff later, I have drawn it out so that you can see that the A squared is going to be located underneath the positive squared value, and the B squared is underneath the negative. So we're no longer, when we're looking at hyperbolas, able to say that A goes with X and B goes with Y, the way that this is stated, right? A is going to go with the positive and B is going to go with the negative. You do? That's good. All right, I don't know how much space I have. I really need to not use black screens on the black backdrop. All right, I'm going to draw 2 pictures for us again. I'm going to start with pictures that actually have dotted reference points anyway. These aren't really the axes, but they are acting that way. Okay, so if we had a center at 0, 0, this would be the X and Y axis, okay? In general, we don't always have centers of 0, 0. Our centers, as a generic statement, are HK. All right, everybody good with that so far? So this HK is going to determine these dotted axes-like images that are showing up. And within them, I'll draw out the first one completely. We have 2 options. So parabolas can open up or down, right? And then left or right. Hyperbolas have the same option. So the hyperbola option is that we could have it opening left and right like this. Or we could have it opening up and down like this. The first one that I drew, where it's opening left and right, is when we have the X squared positive, or first, if you want to label it that way. And the second one is when we have the Y squared positive, or first. That kind of fits a little bit. This, I mean, if we ignored, sort of the bottom half of this, we'd have a parabola shape for being Y squared. So we're focusing on the Y squared being listed first here. And we get the parabola shape that we've mostly used, like in algebra along the way. And then the other one is the opening sideways ones. So a couple of things here to note. We can actually take the A and the B values that we're given, and we can figure out how far away from the center we go in each direction. In other words, we can determine kind of the how sharp the graph is. So let me show you what I mean by that. This distance right here and this distance right here are determined by A. Okay, so those are A's. There's a box, sort of, that's being created here, and there is a distance also that is determined by B. So that distance, and I'm going to kind of pull it further away to try to get my spacing a little bit more spread out, but we don't necessarily know that it's bigger. Okay, this is just a drawing. So this orange value is A, the yellow value is B. And if I were to draw like a box, essentially, that connects, I didn't draw them in though, let me do that first. These points right here in orange and the 2 points in yellow, if I were to create a box through those points so that it looked something like that, let me at least change the color. Right here. What that box would actually tell us is that the corners of the box, right, this is a visual description first, the corners of the box would actually be the lines through which the asymptotes go. So these corners, if drawn well, so let me actually cut these out. I'll put them back in a second. If I've just got the box, it's perfectly symmetric, which this one's not quite. I'll move it over just a little bit, make it a little bit more convincing. Then the corners of the box here and here are going to create lines. And the lines that they create are the asymptotes. So if I draw a line like this through the center and then the two corners of the box that I've created, I actually have the asymptotes of the graph. And the asymptotes act just like every other asymptote you've ever seen in your life. They're graphs, they're lines that the graph gets close to. Right? So that's why what we see happen is we see it how sharply it opens. So it's sort of hugging to these right here. Whoops. Like that. I know not everything's lining up perfectly, but can you picture what I'm trying to draw? Can you kind of see it? If those asymptote lines are less vertical, like they're less steep, then the parabola is also going to be sandwiched tighter on the edges, right? This parabola is hyperbola is opening very broadly because I had really steep asymptote lines drawn in, right? But if my asymptote lines had been drawn in such a way that they were more like, y equal x lines, right? Or something like that, I would have a graph that had much tighter hyperbola branches in between them. Let's label a couple of things. So those orange lines are exactly what I mentioned. They're the asymptotes.
So, just a quick question.
Yes?
The smaller the b value, the more steep it's going to be opening?
It's the relationship between the A and the B. Okay, it's not necessarily how big B itself is, but it's how big it is in comparison to A.
Okay.
Yeah.
So, like, that's, if the relation with A and B is smaller, it's going to have a steeper opening.
Depending on the direction in which you're talking about, yes. Yeah. All right, so we've got the asymptotes listed. Those are good. We've talked about the center being that dot in the center. I'm not going to label that because I'm kind of out of space to label that, but I think you've got that okay. And then the vertices are actually the points that are on the hyperbola that are plotted, right? They're kind of like the vertex min and max, if you will, of these branches that open up to the sides. These are the vertices. Let's see, what else do I want to post? Oh, there's actually foci out here too. I am running out of colors. We're going to go with red. I don't like using red because I think it's hard to read, but we're going to go with it anyway. For drawing purposes, I think it's okay. Those two red dots, those are my foci. They are also on the interior of these branches as they open, just like a foci or a focus is when we do a parabola. They're always on the inside of the shape. Foci, focus are always on the inside of the shape. So these points right here are the foci. Okay, let me mention one more thing on my picture, and then I'll sketch in a little bit down here more, but not much. The foci are C units away from the center. The C value is found by taking the A squared and the B squared and adding them. I didn't actually mention that. I know you filled it in, but I didn't actually mention it. That is how we're going to find the C. So this distance is right here. This distance right here is C. Okay, from the center out to the foci. All right, so let me just make a couple mentions here on the other graph. I'm not going to fully draw it out because it became messy really quick, as you saw. But the distance actually away is still A. It's always going to be A to the vertex, the vertices of my graph. So my vertices are now here, right? So they are up and down from this. So this A will affect the Y value. The center X value will be the same, but we're just going to go up and down from here. I could draw a similar rectangle here, right? It would be a long rectangle this time. I could draw in my asymptotes and so forth if needed. Okay, the asymptotes of a hyperbola. They do have a specific form, and you can, again, memorize this form. I'm not going to, because I'm going to do it from a graph. But if you want it, here they are. So for a horizontal transverse axis, it's the first one, and for a vertical transverse axis, it's the second. You'll notice they both say y equals, they both have x minus h, they both have the k. All those pieces are the same. What's different between the two asymptotes listed here?
Yeah.
A and B. It's flipped, right? It depends on whether the axis is opening along the vertical axis or the horizontal axis. So you have to pay attention to the location for those. That's the only difference when we're looking at those.
So which one goes? Oh, okay, that's vertical.
Yeah.
Horizontal. So like for the horizontal, that's going to be when it's like opening that way, right?
Mm-hmm.
Yeah.
Opening, yeah. Okay. Again, I find all of it a lot easier if I draw the picture and then I identify the pieces from the picture. So that's how I'm going to show it to you. But if you want to come back and deal with equations instead, you can do that, okay? So let me show you an example. This one's actually already in the nice form for us. You don't have to complete the square for this. Let's start with, how will this graph open? Left and right or up and down?
Right.
Left and right. How do you know it's up left and right?
Because x is the first value.
Yes, because the x is first. So this one's going to open left and right. What's the center? 1, 0. So that's actually the first point I'm going to plot. I'm going to plot 1, 0. It's going to be right here. Actually, it's not going to be on my graph. Let me graph it in yellow. 1, 0. Okay. And it's going to open left and right. Now, the value underneath the first component, right, tells us how far left and right we're going to go. It's a 9. Okay, so from this point, we're going to go how much in each direction? 3, right? It's the square root. So we're going to open up 3 away. So 1, 2, 3, and 1, 2, 3. So the points that we're going to plot are going to be here and here, and the hyperbola, I keep using the wrong word, are going to open in both directions from there.
Those are the vertices.
Those are the vertices. So we can list those down because we found them, and it probably asked us to, I suspect. So what are my vertices? -2, 0, and what? 4, 0. Okay, everybody good with those? Okay. I want to actually draw in the B value. This is me wanting to look at the picture of it. What's my B value for this? It's 2. So I'm going to go up 2 and down 2 from the center. So I'm going to put a point right here. Actually, let me do it again in yellow because it's not on the curve. This yellow point and this yellow point. And I'm going to draw in as small as I can. I'm going to make it a very thin point. A box where I get the corners of this drawn in. So there, I'm trying to do it as very thin and fine as I can. And I'm going to include this corner and this corner. And that's going to be one of my asymptotes. And I'm going to do the same thing for this corner and this corner. These are the 2 asymptotes I'm going to get for my graph. So we're going to do our best to connect through here. That's one of my asymptotes. And connect through here. And we're going to see a really tight hyperbola when I draw this one, right? Because of the way that this is opening. Now, if it were opening up and down, it'd be broad. But because it's going to be opening left and right, it's going to be tight. I can sketch in how the graph opens pretty quickly here. It's going to open something like this. And I believe the only thing I haven't actually done is find the equation of the asymptotes. Agreed?
Also the focuses.
Oh, I didn't do the focuses either. Thank you for that. Yes, forgot that one. Focus and the asymptotes. Okay, focus and asymptotes. So let's actually use the C value to find the focus. So C squared is equal to A squared plus B squared. So that's 4 and 9. So C is actually the square root of 13. So my foci are going to take the X value, which was 1 from the center, and they're going to add or subtract the square root 13, which doesn't simplify, and have the corresponding Y value. If you want to write them as 2 separate order pairs like I did last time, go for it. But I'm going to write them as combined this time. Okay? The asymptotes are the last things that I need to actually do. You can count the slope of this very easily from the graph because we've drawn it well. What is the slope if I take this center and go up to this corner? Rise over run. It's up 2 and over 3. It went over 3. It's up 2 and over 3. That slope is 2/3, right? So for this one, m is 2/3. And for the other one, it's the same thing, but negative. So m is negative 2/3. And then I have an ordered pair. I might as well use the center, right? The center of my equation is -1. So y minus 0 equals 2/3. And then I have x minus 1. I'll simplify in a second. And then y minus 0 equals negative 2/3. And it's x minus 1. So this is y equals 2/3, x minus 2/3, and y equals negative 2/3 x plus 2/3. And those are the equations of my asymptote. And I did it visually. If you want to go back to the formulas, you can. It's not going to hurt anything, but you're going to have some formulas to actually process through then. Ben, do you have a question?
Yes, would it be acceptable to say y equals plus or minus 2 over 3 times x minus 1?
The problem, yes, but you're going to actually have to write them out, and one of them will distribute positive and one of them will distribute negative. And it's possible to write this as plus or minus 2/3 x and then minus or plus 1/3, but it looks, or minus or plus 2/3, but it looks weird, right? So if you were writing it, it would have this kind of a form. Which is super awkward, and I don't know if there's going to be any tools that are going to allow you to do that in WebAssign. So they're probably going to force you to draw 2 different equations. Okay, we'll stop there for today.